researcher. To his credit, he has more than 100 research publications in the highly cited journals with international repute. He has received many prestigious awards, including NASA Group Achievement Award, INSA Award. In addition to that, he is the lead author of the IPCC Fourth Assessment Report. Today, we are fortunate enough to have Dr. Ramachandran, a senior professor, a scientist par excellence nationally and internationally to this winter school. The topic that he is going to present is the aerosol. The aerosol is an exciting research topic, not only because of its obvious importance to the society, but also because of aerosol research draw on many branches of sciences. The chemistry of air pollutants, the physics of weather, the biology of emissions from tree, and the computer science need to make predictions. It is highly challenging field of research that puts students in a simulating environment, working with a wide range of different scientists. On behalf of the UGC Stride Organizing Committee, I welcome our eminent speaker. With this program, I hand over this session to Professor S. Ramachandran for further proceedings. Thank you, sir. Sir, unmute பண்ணிருங்க. You.
Okay, thank you, Dr. Bhaskar. I am indeed very happy to be a part of this UGC Stride, the Winter School on Climate Change. So today, as Vijay mentioned, I will be talking about aerosols, why and how they are important, their several characteristics, etc. Giving you a bird's eye view of about the topic and the topic of research and what is happening in the world, what are the challenges, etc. So I will be very happy. I don't know how the format is, but I will be very happy if I'm interrupted and asked questions in between. I don't mind it, and I have no problem for example, when I am interrupted or not. So since this is going to be a beneficial presentation or beneficial winter school, I request all the participants to utilize it to the maximum. So with this brief introduction, let me go to the presentation. Is the screen visible to all of you?
Yes, sir, it is.
Okay. So is my voice audible to all of you?
Yes, sir.
Okay. So the title of the lecture is Aerosols and Climate Change. So I will begin with an introduction on climate, and then move on to what we mean by climate change, and then discuss a lot about aerosols, and then we'll finally summarize the lecture. When we say climate or the climate system is a complex interactive system. So, which involves the atmosphere, the land surface, snow and ice, which we call as the hydrosphere or the cryosphere, and then the oceans. So you can see that there are several constituents that are present in the different spheres that you are seeing here, from atmosphere to the ocean, cryosphere, etc. So when you say a climate, it is the long term, typically about 30 years average of what we call as the weather. Weather is a day-to-day phenomenon. Like yesterday it was warmer, today it is colder, that is the weather. But if you look at this weather, take an average for about 30 years, then you will end up in what is being called as a climate. So then the immediate question is, what do you mean by climate change? So it means the change in the state of the climate that can be determined by changes in the mean and or variability of its properties. When I mean properties, all these are properties. For example, and the changes in the solar input, clouds, the surface water, rivers and lakes, changes in the sea level circulation, biochemistry, ice ocean coupling, all of them. How is the air-sea interaction changed, etc. Any of these parameters which are supposed to be operating at a stage, so wherein the present climate is maintained, if any of this composition, any of these properties get changed, then it will actually result in what is called as a climate change. And please note that climate itself is about a 3-decadal average of the weather. So when we say climate change, then it should also persist or last for an extended period, typically on the order of about decades, just like the weather. So many of this at the first instance may sound Greek and Latin to you, but don't mind. By the end of this lecture, I'm sure you will be able to understand what I meant by this. So as you all are aware that you might have heard before in this school that the solar energy is the main driver of the Earth atmosphere system. So we need to see whether is the atmosphere radiatively balanced. As most of the physics and chemistry students who are attending this course will know, that in order to maintain radiative and thermal equilibrium, what is coming in should be what is going out. So if you look at the global mean Earth atmosphere radiation budget, which is drawn here. So if you look at the top 3 numbers, what is coming in is 342 watt per meter squared. The radiation is measured in watt per unit area. So that is why it is called watt per meter squared. And then what is going back is 107 plus 235. So that is equal to 342. So the immediate question that will come to you is, well, what is coming in is what is going out. I mean, why you should be bothered about it. We will see that. Hold on patiently. We will see why we should be bothered. So first, let us look at some of the features of the Earth, the radiation that we are receiving. So 342 is coming in, out of which 77 is reflected by the subject matter of today's interest, namely aerosols, clouds that you see, and other gases, including air molecules. And then the surface reflects about 30 watt per meter squared. Both of them combined, it comes to 107 watt per meter squared. 107 by 340, 107 is the radiation that is reflected back by the Earth's atmosphere immediately, as soon as the radiation is received. Now this ratio, 107 by 342, roughly translates to about 0.3 or 30%. And this is called as the planetary albedo. The ratio of the radiation that is reflected back by the planet with respect to what is coming in. So the radiation, the remaining, whatever is coming in, for example, is some of them is absorbed by the atmosphere, and then the long wave. So whatever is coming in is actually in the short wave or the visible region. As a function of altitude, if you see the ultraviolet and all, those radiation gets absorbed in the higher altitudes of the atmosphere, while the radiation that is between visible, mostly visible, they come to reach the Earth's surface. And out of the radiation that we are receiving from the sun, about 45% of the radiation is in the visible band. The remaining, all covering from ultraviolet to all the way X-ray, microwave, etc., they fight for the remaining 55% of the radiation. So the radiation that we are receiving from the sun, some of them is absorbed by the atmosphere, and then the Earth will also reflect the radiation back after this due process of interaction, namely evaporation, with thermal heating, etc. So if you look at the outgoing terrestrial radiation, which is 235, plus reflected solar radiation, which is 107, that is equal to the incoming solar radiation. So the Earth is in a thermal radiative equilibrium balance, in the balance of this one. Okay. But we also know that actually this is not the scenario currently. So in order to appreciate that, first we should understand the difference between what we call as the greenhouse effect and what we call as the global warming. As many of you are aware that the natural greenhouse effect is the warming of the Earth's atmosphere due to the presence of the background greenhouse gases, primarily water vapor, which is a natural component, carbon dioxide, methane, ozone, nitrous oxide, and methyl chloride. Because of this natural greenhouse effect, the Earth's surface temperature is a livable 14 to 15 degrees centigrade. Otherwise, the temperature would have been minus 18 degrees centigrade, which is too cold to support any form of life. Global warming is the increase in the Earth's temperature above the natural greenhouse effect temperature as a result of the emission of the man-made greenhouse gases, including carbon dioxide, methane, nitrous oxide, ozone, and aerosols, the topic of today's subject. Most of you may be aware that aerosols are solid or liquid particles that are suspended in air, can be of natural or anthropogenic origin. As Vijay pointed out, the science of aerosols involves physics, chemistry, math, biology, and engineering. So the sources of these particles are different. They are both natural and man-made in origin. Because of this production mechanism, they are emitted in different sizes. And because of the physical process that happen, they change their sizes. So the production source determines the size of the particle, while the production mechanism determines both the size and the chemical composition. So when I mean this, for example, when it is a vehicular emission or an industrial emission, we know the source. Typically the gases that are emitted, they get converted into particulate matter, and these are typically in the fine mode, particles of size or radius less than 1 micrometer. While if you look at the dust that is coming from the desert or sea spray or sea salt from the ocean, these are typically are bigger in size. So the production source tells you the chemical nature of the particle that you will have in the atmosphere, while the production mechanism will determine how chemically these are important. So here we are looking at pictures of aerosols, of different kinds of aerosols. All of this we'll see in detail. So we also divide this in terms of the sizes, namely nucleation, which is 0.001 to 0.1 micrometer. Accumulation, because the particles come together, coagulate and accumulate. These are typically of particles that are sizes between 0.1 to 1 micrometer. And then the particles which are more larger, more bigger in size, greater than 1 micrometer in radius, they are called as the coarse mode particles. So in order for you to appreciate what we are talking about, here I have drawn a comparison figure, what we call as the pollutants or aerosols in this case. Let us try to compare it with the dimensions of a known quantity or known aspect in our lives. So if you take the human hair, it is roughly about 50 to 70 micrometer. But And if you take the grain of sand, for example, which I said as the quartz, so these are typically larger than the dimension of the human hair. But if you look at particulate matter that is less than 2.5 micrometer in diameter, these are such small particles with respect to what is the dimension of the hair. So when you look at the natural sources, which is both dust, pollen from biological origin, fungal spores, etc. These are on the order of about very close to greater than 1 micrometer and less than about 10 micrometer. So this is the dimension of these particles. So we are talking about such small particles that are present in the atmosphere when compared to the dimension of the human hair. This is just a comparison for you to appreciate what we are talking about. So coming to the basic physics of it, the properties can be divided of these aerosols can be divided into physical, chemical, optical, which finally will determine the radiative capacity or the radiative properties. Physical, when I mean the size, the shape, the texture, how is it quartz, etc. Chemical, because as I said, the sources are different, the particle nature is different. And so optical, depending on what it is, what type of particle, whether it will scatter or absorb, etc. That is determined by the optical characteristic or optical capacity of the particle, which is emitted in the atmosphere. When it comes to radiative, this is a combination of all of them. The size, the chemistry, and the optics, they determine how much of the radiation that is coming in will be scattered versus how much of the radiation that will be absorbed vis-a-vis what is coming in. So if I am asked to find out why do we need to study these aerosols, for example, like in any other branch of science, basic information about these particles which are present all around us is necessary. The second thing is, as you will see as the lecture proceeds, that they play a very important role in the Earth atmosphere radiative budget and on climate. So in order for these two to be done, we need to study these particles. Now, in the earlier figure, we saw that depending on the sizes, these particles are classified as nucleation, accumulation, and quartz. How are these particles produced? The different physico-chemical processes that are involved in making these particles in the atmosphere, as we saw, the sources are from natural to man-made emissions. The particles which are in the smaller size range, which we call as the nucleation, these are typically the hot vapors that are emitted by the precursor gases such as sulfur dioxide, nitrous oxide, nitrate, sulfate, etc. They condense on the particles and then they coagulate to form particles in the nucleation size range. Now, when the particles are formed, the amount of time that they can reside in the atmosphere is dictated by the mobility of these particles and also the chemical kinetics or chemical characteristics of this particle. So typically the lifetime is of the order of a few hours to maximum a day in the atmosphere for this size particles. So what they do is actually they accumulate and then they graduate to the next size range, which is the accumulation size range. So which is nothing but the particles that are present here will condense and then grow. This condensational growth of nuclei and how they convert chemically from of gases to low volatility vapor, and then so they form actually what are called as the droplets, meaning sizes that are of measurable and a stable size range. That we call as the accumulation size range. In comparison, the natural aerosols, they are mostly of a bigger size range, more than 1 micrometer in diameter, typically. But It need not be universally true. For example, the wind-blown dust from desert areas, from dry arid regions, wherein and also over the land surfaces where the activity is disturbed by the disturbance of the soils, etc. They all contribute to what is called as the dust, wind-blown dust. The mechanically integrated emissions, sea spray, people who are participants who are from the ocean or have gone to the beach would have realized that when you go across and take a lateral view of the ocean surface, you see a lot of foam kind of a material that is coming up, and you are seeing this like a haze. These are nothing but sea salt particles, sodium chloride, that is generated by the waves, the winds on the ocean surface. They form a jet and then they break into these particles and then they get thrown into the atmosphere. So that is the sea spray that you are seeing. Volcanoes, which we will see later, volcanic eruptions inject a lot of these particles into the atmosphere with significant radiative, dynamical and climate impacts. We will see that later in the proceeds of the talk. And then plant particles, which are typically larger in size. So I'm sure you are familiar with people saying that, well, this is very cold and I went out for a walk and then this has a lot of trees and I went to the park, but then I feel very kind of stuffy and smoky. These are because of the pollen that is emitted by the plants. All of them, they contribute to particles that are in the square size range, which we can actually breathe in or inhale. And so these are also aerosol particles. But when you compare the lifetime, the residence time of these particles that they can be present in the atmosphere, typically this is about a few hours to 1 day. This is the more stable size range wherein the particles can stay in the atmosphere for about a week. And these also are, when the particles are larger, they feel the effect of gravity or sedimentation more stronger than the smaller size particles, and hence they also settle from the atmosphere quickly in the lower altitudes. But when you go to the higher altitudes, the story changes, as you will see in the next transparency. So when these aerosols are produced, you are familiar with these pictures that we call as the brownish material that you see is what we call as the haze or the aerosol distribution. So typically, if you look at the classification of these particles that are present chemically, so we can classify them as sulfate, nitrate, sea salt, mineral dust, black carbon, organic carbon, etc. And here you are also seeing the distribution of natural sources versus the man-made anthropogenic sources. At the background, you are also seeing that this white is getting faded to black as you go from natural to anthropogenic sources. That indicates that the particles that are produced by man-made sources are more absorbing than the particles which are produced by natural sources, which are scattered, more of which we will see later. So another important role that these aerosols play in the atmosphere is the following, that without these aerosols present in the atmosphere, no clouds will be present. No aerosol means no clouds. How does it happen? The condensable vapor that we saw while the aerosols are formed, they can condense on a bigger particle and then form a bigger cloud particle. They can nucleate and then coagulate with other particles and then condense and then can form what is called as the cloud condensation nuclei, meaning cloud bearing or which can actually bring the rain. These are typically smaller in size. So when you see the cloud as a picture, this contains a lot of droplets of this size, about 100 nanometers, which condense and coagulate. Then this is another scenario that we are all familiar with between a cleaner situation, be it in Madurai or Madras or Delhi or anywhere else in the world. that the difference between a cleaner atmosphere versus a polluted, a hazy atmosphere. You can see that very clearly that we also measure the, as you have heard, when you are flying in the aircraft, the captain or the pilot would say that this is the visibility now and all that. So this is actually what he is referring to is a measure of this distance, that whether the atmosphere is cleaner, so the visibility range increases or the visual range increases, while the atmosphere is polluted, then the visual range decreases. So you can see that this is also synonymous with the number of particles that are present. So in a cleaner atmosphere, it's about 1 microgram per meter cube, the mass of the particulate matter. But as the situation deteriorates, you see that the number of particles increase drastically from 1 to 16, but it can go even more than 100, 200 as the sampling has happened over Delhi as of today because of various reasons. So there's another measure or another parameter that you can actually see for yourself how the nature is changing because of the pollution. So this, I'm sure this is a hot topic now, effects of air pollution on human health. So these are the cities with the annual mean PM2.5 measurements. The 24-hour PM10 standard, meaning the presence of particulate matter that is less than 10 micrometer, according to the World Health Organization standard, should be about 150 micrograms per meter cube. Most of the urban cities in India, as you may be aware, is actually having particles that are greater than this level. And you can see that. I mean, it's a story across Asia almost. So why are we concerned about it? Because they pose a serious health risk, because it can travel into the respiratory tract, and particulate matter that is 2.5 micrometer or less than that is more dangerous because it can actually penetrate into the lungs and sometimes even into the bloodstream. So now, for example, though the research on this COVID virus being which will increase the effect of this due to air pollution, there are results that are coming in of different nature. But one way or one mechanism is this virus getting associated with the particle, and the particle you kind of inhale because the particles are present in the atmosphere. They don't go away because of the current weather conditions when it is cold, for example, as it is in Delhi. So what are the health effects that will result because of this? It is the function of lung will decrease. It can result in chronic bronchitis, respiratory symptoms. It can also regulate the change in the regulated heartbeat, etc. It can result in. So which are the groups that are sensitive to these particles? In fact, everybody on Earth. So here we are saying everybody, like people with heart or lung disease, older adults, children, pregnant women, almost all of them. So, okay. Now, how do these particles, do they uniformly are the same throughout the Earth at every location? The answer is no, because we know that the sources of these particles are different and they come from different regions, etc., different sources. So typically the mass, and the concentration, the number, and also the size, they vary. So here we are looking at 6 different environments over the continent, or the urban region, rural, or the ocean, or desert, and compared to Arctic, which is kind of a cleaner atmosphere, just to emphasize the aspect. So what we are seeing is that typically the mass increases as the size of the particles also increase. For example, if you see that there is a gradual increase in the size of the particle as you go from a continental, meaning more cleaner when compared to urban, when compared to rural, when compared to maritime, etc. But look at the concentration. Urban is the one where the number of particles are larger as compared to a continent or ocean or rural, etc. And mass, which is a derivative of all this, you can see that similar differences are occurring. Keep that in mind when we are discussing several other features of these particles over different environments. So this we looked at briefly during the previous two transparencies. Regarding the lifetime of these particles, how long will they be present in the atmosphere? Now, this is a function of the size, the process that is involved, and also it's a function of the altitude. So, what you are seeing is on the x-axis is the particle radius, which we talked about, that aerosols can be from 0.001 micrometer to about 100 micrometers or so. And as a function of altitude, how the numbers typically vary. So in the near the ground, there will be more number of particles. There will be about 10,000. As you go up in the atmosphere, you see that this decreases to 5,000, then 500, and then when you go to altitudes about 20 kilometers or so, there are hardly a few particles. Now, you also notice another thing, that the size range of particles, they change as the altitude of the atmosphere increases. So here at the Earth's surface, which is actually the source region of most of these particles, you will see particles of all sizes that are present. But the numbers are different. Some may be more, some may be less. But as you go up in the atmosphere, because of this process of gas to particle conversion, coagulation, condensation, and mechanically when these particles are produced, as I said, they can disintegrate and feel the effect of gravity and then they settle down. The particles in the lowermost range as well as in the coarse range will actually decrease as you go up in the atmosphere. And you go further up, it will still further decrease. You can see that the size distribution or the distribution of these particles forming a conic structure. Now look at the residence time. Here it is on the order of a few hours going up to a day, what is called as the boundary layer, which is on the order of about 1 or 2 kilometers in the atmosphere. And when you go up in the higher altitudes that are higher than that, in the troposphere, for example, it can stay up to a week. And then you go further up in the stratosphere, altitudes above 15 kilometers or so, it can stay up to more than 1 year or up to 3 years. Another important aspect that we need to remember is that all these aerosols, whatever we are talking now, are present in the altitudes between 0 to 40 kilometers. 99.9% of these particles are present in these altitudes. There are also other sources such as the interplanetary dust, dust from the interstellar medium, etc. But the percentage of these contributing to the aerosols that are present in the Earth's atmosphere is actually much less than even 0.1%. So for practical reasons, you can ignore them and not worry about it. So we are talking or focusing on particles that are present between from the surface to 40 kilometers. The other major difference that comes in terms of the altitude regarding the aerosols is that the types of particles that are present in the lower altitudes up to the troposphere are different than what you actually see in the altitudes above, meaning stratosphere. So in the troposphere or on the Earth's surface, you can see black carbon, dust, sea salt, sulfate, nitrate, organics, etc. But when you go to the stratosphere, you will see almost all of the 100% is actually the sulfate type of particles. Okay, so we looked at the mass, we looked at the concentration, now and also the typical size of the particle. When you measure, when you say that this aerosol is found over the land or the ocean or urban versus maritime, then it is actually made up of different types of particles. They are made up of different types, and as we know, the sources of these particles are different over land and ocean. So if you consider the land, for example, you will have water soluble, which consists of sulfate, organics, nitrates, etc. And then you also have insoluble soil particles with less amount of organic. and then the black carbon, which is emitted from the industrial vehicular activities or emissions. So, as a function of radius on the x-axis, what you are seeing is the number, and what is given in red is the total, which is a summation of the sulfate, nitrate, organics that are present, the insoluble species, namely soil material, and then the black carbon particles. Each of them, they have a different size range. For example, insoluble is more like the particle, as we know, that this is made of soil material, which means the particles are larger in radius. But they are also less in number when compared to the sulfate or the black carbon emissions. Now, the moment you go to ocean, first thing that strikes is that look at the number of particles that are present here, that it's an order of magnitude more over land when compared to the ocean. You see that this is about 10 to the power of 6 or less than that. This is going all the way up to 10 to the power of 7. And then you also see that apart from the sulfate that is present and the black carbon, you also have the major component of the ocean, which is the sea salt particles that are produced by the bursting of the bubbles on the ocean surface, and then they produce these, and then they result in the atmosphere. They eject into the atmosphere. So they have a different size distribution. So like, for example, as is shown here, whether it is in the sea salt particles on accumulation mode or Quer's mode, etc., this will also change. So if I am asked to condense all these particles and then say that, okay, over the globe, how does it look? So here what we are using is one of the key aerosol parameters that we use, which is nothing but, which is called as the aerosol optical depth, which is nothing but integration of all the particles that are present between 0 to 40 kilometers and in the size range of somewhere from 0.01 to 10 micrometer. And depending on what is scattering, size distribution aspect, and how much is scattered, how much is absorption, etc., it's also a function of the wavelength. So, so this we are seeing it at like 550 nanometer or mid visible or 0.55 micrometer. So this is for 4 different seasons in the year, namely winter, pre-monsoon, monsoon, and the fall or post-monsoon. So the values are shown between 0 to 1, and ignoring the numbers, the more redder or pinkish it is, the number of particles are higher when compared to the blue or the purple. Keep that in mind. So first thing that you see is that the distribution is not uniform, and you also see that there are regions where the optical depths are high. Third is that this also changes as a function of the season. So for example, if you compare the pre-monsoon versus the monsoon, you see that the pre-monsoon high over the Indo-Gangetic plain, over East Asia. When you look at monsoon, for example, you see a lot of reds over the African region also, and there is also a lot of transport that is associated with these particles. And you see this scenario changing when it comes to the post-monsoon. Over the ocean surfaces, especially in the southern hemisphere, during the post-monsoon season, the wind speeds are very high. So this will result in a higher amount of sea salt particles, leading to a relatively higher optical depths when compared to, for example, either monsoon or in the pre-monsoon, than in the winter and the post-monsoon. Now, while the optical depth or the aerosol optical depth or AOD, it gives you the total column concentration of the species that are present in the atmosphere without any distinction as to how much is sulfate, how much is nitrate, how much is black carbon, etc. The single scattering albedo is actually the ratio of how much of the AOD that you measure is of scattering type versus how much of the AOD that you measured consists of both scattering and absorption, which is called as the extinction. So it's a ratio of scattering to extinction. Extinction is a summation of scattering plus absorption. For a perfect scatterer like sulfate or sea salt, this ratio will be 1 because the extinction is entirely due to scattering and 0 by absorption. So AOD scattering by AOD scattering will be equal to 1. But for black carbon, let us say, or for dust, depending on what the species is, it has both scattering and the absorption. So scattering will not be equivalent to extinction. In that case, this ratio becomes lower. For dust, it is 0.84. For black carbon, it is 0.21, which is the single largest absorber, aerosol absorber in the atmosphere, in the mid-visible. Now, there is another parameter that goes with this aerosol species, which is when the radiation interacts with this particle, how much of this radiation is forward scattered versus how much of the radiation is back scattered. When I say forward scattered, I am looking at the sphere in terms of the sphere between 0 to 90 degree versus back scattering, that is from 91 to 180 degree. Okay, so this is a ratio, or is the when the radiation interacts with this particle, how in the 180 or 360 degree frame, how the radiation will be distributed. That is measured by the asymmetry parameter. If the radiation is equal in both the spheres, radiation that is scattered is equal in both the spheres, then it is actually symmetric, like it happens in case of the air molecule scattering. The radiation that is scattered in the forward direction is the same as the radiation that is scattered in the backward direction. So that scattering is called as a symmetric scattering. And as you may be aware that the dipole, scattering by a dipole is symmetric as it happens in case of the air molecules or Rayleigh scattering. But this whole thing changes when you have the size of the particle that is larger than the air molecule, just like the aerosol species. Depending on the size, it can be bigger. So for bigger particles, the asymmetry of this radiation also increases. So while single scattering albedo depends on the chemical composition, the asymmetry parameter depends on the size distribution that we saw before, like what is it made up of, whether it is made up of, the distribution is made up of larger particles or smaller particles. Depending on that, the scattered intensity will be higher or lower. Okay, now we looked at the global map of the optical depth. Now we also defined what is the chemical, based on the chemical composition, what is the single scattering albedo. So here you are looking at, in contrast to the optical depth, the single scattering albedo. The single scattering albedo, as you are familiar with, is the ratio of scattering AOD to the extinction AOD. In contrast to the map that you saw, where the optical depth varied from 0 to 1, which varied from blue to red, here I have actually reversed the whole sequence. Here the graph runs from about 0.83 to 1, and the more absorbing particles are shown in red, while more scattering, because you are familiar with the blue sky, scattering, etc. When you have more scattering, then your sky looks more blue. So if you look at this, immediately it is very clearly visible that the composition also varies, just like the columnar content of these particles in the atmosphere. So, and they can be of different types depending on the season, depending on where they are, etc. So if you look at winter, for example, over Africa, you see that this consists of a large amount of absorbing particles, which are due to biomass burning activities and the emissions that occur because of that, and then which also is present in the monsoon season. But in the pre-monsoon, it decreases a little less. And then when you go to during the you remember this, that there is a lot of transport that is associated with this. We can see that similar signature is present here when these particles are more of the absorbing type when compared to the scattering type. You can also see that this the aerosols that are present over Africa are kind of always absorbing when compared to the other regions which exhibit a seasonality in their scattering or the absorbing contribution. So mainly urban industrialized regions of the northern hemisphere, and also, for example, including Africa where biomass burning is predominant, you see more of these absorbing particles. And when these particles are transported like it happens here, you will also see them over the oceanic region. So why do we need to study? Why do we need to know that? As I mentioned, that not only the basic information that we have come to know so far, it's also important to know how they affect or influence the climate by changing the radiative balance. So in this aspect, aerosols play two different kind of forcings or impart two forcings on the atmosphere. One is the direct radiative forcing, the other is the indirect radiative forcing. When I mean direct radiative forcing, this is, as we saw before, it is by scattering the radiation that is coming in or by absorbing the radiation that is coming in. Now, please note that the radiative effects over the region is different when the radiation is interrupted by scattering aerosols versus the absorbing aerosols. When the radiation from the sun is interrupted by particles which are scattering, for example, sea salt, sulfate, etc. One commonality is that whether it is the absorbing aerosol or the scattering aerosol, because of scattering or absorbing, the amount of radiation that reaches the Earth's surface will always be lower, will decrease, be it absorbing or be it scattering. One would have scattered, the other would have absorbed. So that is the first commonality, but remaining all are actually differences. So once in a scattering aerosol dominant distribution or over a region, it will because of this less radiation reaching the surface, it will produce a cooling, and then when the atmospheric circulation due to dynamics and winds and mixing processes, it will actually spread the cooling that is formed both in terms of the altitude, vertical, as well as in terms of the regional scale. But contrast this with absorbing aerosols. So it will produce a localized cooling because of less radiation that is reaching the surface, but the same atmospheric circulation and mixing here that it produced a cooling over the region, it will actually redistribute this warming that is up above the surface. And then over a period of time, it will actually result in a homogeneous or a warming across the region and also in terms of the altitude. So this is a basic difference between scattering aerosols and absorbing aerosols in terms of the radiative effects. And both these processes are the direct effects of interaction of radiation with the aerosols, because it is directly scattering or by absorbing the radiation. Now, when it comes to, so I mentioned in the preliminary discussions that without aerosols there will be no clouds. So these aerosols can actually alter the properties of the clouds. So this is where these particles indirectly contribute to the radiative effects. As you know, that clouds are the cooling agent in the atmosphere. They always produce a cooling in terms of the radiative balance. So let us look at some of these properties. For example, in a cleaner environment. So we saw that these are the aerosols become cloud condensation nuclei and attain a certain size, and then they will produce the rain, etc. So you can see in a cleaner environment, the blue dots or circles that you see are the cloud droplets, and you also see that there are some few red dots. Okay, and these are actually the aerosols, but the blue ones are the cloud droplets in the cloud. So you also see the dotted lines, which is actually the amount of precipitation of the rain. Compare this with the polluted environment. So what is striking is that the number of red dots have increased because it is polluted, and you also see that the cloud droplets have shrunk in size. Okay, from about 50% to almost 25% or so. So because of this variation, what happens is less radiation will reach the surface. It will also it will have more reflection. These clouds will reflect more, and so the cloud droplets are smaller. It will actually result in less precipitation. So these aerosols, depending on whether they are present over a cleaner or a polluted environment, modify the optical properties and lifetimes of clouds, and therefore will also modulate the precipitation or the rainfall that is occurring over a region. Now, the other effect that happens very significantly is that when we saw that when the absorbing aerosols interact with the radiation, first it will produce a cooling at the surface, but as a function of altitude, it will actually produce a warming. And precipitable clouds that we are familiar with, the rain-bearing clouds, typically they are in the range of about 1.5 to 2 kilometers. And these aerosols coming in the troposphere, for example, they all can be found, most of them, in the first 5 kilometers of the atmosphere. So when you have a dominant black carbon contribution, which we saw is the single largest absorber of radiation, then it will actually produce warming. So when the warming is produced, it will actually shrink the cloud droplets that otherwise would have been of this big size. So the shrinking of cloud, which means that the cloud droplets are evaporating. Because of this absorption, the precipitation will also reduce. So to sum up, where connecting aerosols with climate, it is kind of omnipresent species or ubiquitous that is present, that it alters the influence of the atmosphere in all the possible ways, be it through physics or the chemistry, dynamics, precipitation, radiation, etc., from different sources. Now, we saw what is climate. We kept talking about climate. How is this climate determined? And we also saw that there are several components that actually determine the climate in the Earth's atmosphere, or the Earth. And we saw that there is a radiation budget, what is coming in, what is going out, there's a balance, etc. We also talked about global warming. So the global climate, as we know, is controlled by or is influenced by several agents that are both natural and man-made. Okay. So we know that the man-made one, the primary one is the carbon dioxide, and we also know that aerosols, mainly the man-made ones, etc. So what we are seeing here is the radiative forcing. Why it is called radiative forcing, I will describe in the next transparency. But keep this in mind. We already saw that the radiation is measured in watt per meter squared, etc. The forcing is also given in terms of watt per meter squared. So you are familiar with the warming. This is a zero line, and you are familiar with the warming that is produced by carbon dioxide, methane, halocarbons, nitrous oxide, etc. Now, when it comes to the aerosol species, you see that there are different particles that we know, like mineral dust, sea salt, sulfate, nitrate, organic carbon, black carbon, etc. Now, in contrast to the greenhouse gas, which is mainly carbon dioxide, you see that the warming is only in one direction. I mean, the change in the forcing is only in one direction, which is one of warming the atmosphere. But when it comes to aerosols, you see that this forcing or the radiation effect is actually on both sides, cooling as well as it's lower than zero and higher than zero, meaning it is cooling as well as warming. We know warming is done by black carbon, while other species will actually, mainly they are scattering, and they will reduce the temperature and hence it will produce a cooling. Now, this is the direct effect which we saw of different species in the atmosphere. We also saw that these aerosols will alter the cloud characteristics, like we saw in terms of the evaporation of cloud droplets or modifying the cloud properties, etc. So that is given in terms of what is called as the indirect effect, indirect radiative effect. Now that is one of cooling, but it is also largely very uncertain. The horizontal bar here in each of these represents the uncertainty of these forcing calculations. And so the immediate question will be, well, are there no natural changes that are controlling, that are occurring in the last 1,000 years or so that is contributing to climate change? The answer is that it is actually very minimal. So changes in solar irradiance, for example, which is the natural component, the change in the last 300 years or so from 1750 is almost negligible. It's nothing there. And the albedo change due to land use land cover changes, which is actually very small also. And one thing that is striking is, with respect to the last 50, 60 years, vis-a-vis the previous 200 years, the changes in the forcing has been significantly higher in the last 50 years when compared to the previous 200 years or so. Meaning that the rate of warming, the rate of growth or increase in temperature is significantly faster in the last 100 years or 50 years when compared to the previous 200 years or so. So radiative forcing is nothing but a measure of how the energy balance between what is coming in and what is going out, that is received by the earth, is altered. When factors that affect the climate, which we saw a list of them, how they get altered. Now, why it should be called radiative forcing? Because these factors change the balance between incoming radiation and the outgoing infrared radiation within the Earth's atmosphere. And please note, this is the balance that controls the Earth's surface temperature. And why do I call that forcing? I could have said something else like a different state or a pushing this. No, I call that as forcing because this is to indicate that the Earth's radiative balance is being forced or pushed from its natural normal state. So we have seen this before, how the climate change per se occurs because of the components that are present. These include direct and indirect changes in climate change drivers, which include changes in the greenhouse gases, aerosols, cloud microphysics, and solar irradiance, which directly impart the radiative forcing. There are also non-inertial radiative effects, such as changes in the evaporation mechanism, etc. These are initially radiative effects are initially are present, but then later as the time progresses, they also will contribute to the climate change. So the perturbation and when you look at the climate perturbation and response, you see that the global and regional temperatures will change, vegetation changes, extreme weather events occur, etc. Now, these can be given or produced by natural influences, namely solar process, changes in the orbital motion of the Earth, volcanic eruptions, etc., or human activities from fossil fuel burning, industrial process, changes in the land use activity. They all can produce this direct or indirect changes, which will finally result in climate perturbation and response, which will change the mitigation process, and this will change the human activity, etc. So this is a very closely coupled system that, as I also pointed out earlier, that any change in any of these small component, which we consider as small, is going to result in an effect that is going to have an impact on the lives of the people. So we keep saying that the earth is warmed by a certain temperature, right? So the immediate thing is, but we know that we looked at the radiative balance, and we know that there is a certain amount of radiation that is not going back. It is trapped in the atmosphere, and that we call as the global warming. So the change in the radiative forcing is related to the temperature through this equation, which is the global mean surface temperature response, delta Ts, is proportional to the radiative forcing that we saw before, the net radiative forcing, which is on the order of about 3 watt per meter squared or so. If you put that number, then actually you will see that the earth has warmed by about 1 degree centigrade in the last 100 years. Okay, now how do we do that? I mean, how do we say that this is due to natural or man-made emission? So the figure that you are seeing is the observed trend across the globe in the last 60 years, 1951 to 2010, where this is red, yellow, etc. It's all more is warming, while regions that are blue or gray are actually cooling, which you see much less than the red and the oranges. So means almost the entire globe is warming up. So first let us try to put the natural causes or the changes due to natural phenomena that would have contributed to the change in the temperature or the climate. There are two known natural causes of changes. One is the solar irradiance, the other is the volcanic eruption, which we will see about in the next 1 or 2 slides. We saw in the forcing figure that the changes due to solar irradiance is actually negligible. There is nothing that is contributing. The volcanic eruption, so on the right what you are seeing is the temperature anomaly. In the last 1860, so 150 years or more, that is in black line are the observations, the anomalies with respect to 0, while in blue and red are the model simulations. CMIP means coupled model intercomparison project 3 and 5. And the shades that you see in blue and orange are due to the model variations. So we use typically more number of models in order to find out the kind of a correct picture or so. So this is the resultant of about 30 global climate models, where we take the present day atmosphere and try to simulate it, continue to simulate it for about 200 years, starting from 1850, and then with no change in the condition, and then you make another set of model runs for the same 150 or 200 years, wherein we input the observed changes in the solar irradiance and the changes due to volcanic eruptions. And then the difference between this run with the inputs that are provided by changes in the solar irradiance and volcanic eruption is compared with the run with no input on solar irradiance or volcanic, no change. So that will give you the difference due to the addition of changes in the solar irradiance and volcanic eruption. So we do that and then we plot it. We see this is almost a straight line here. So mainly because there is no change in the solar irradiance we saw, except that when there has been a volcanic eruption, you see that the temperature actually dips. It becomes, the Earth's surface becomes cooler. But otherwise, which is a transient phenomenon, it lasts for about 2 to 3 years and then it comes back up normally, naturally. So if you ignore the small changes in the cooling that is associated with the volcanic eruptions, you see that it's almost a straight line. In the last 150 years, The temperature, meaning that the temperature change that you are witnessing here, shown in black, is not due to the natural changes. Okay. Now, let us now put the changes due to man-made emissions, which includes greenhouse gases, ozone, aerosols, etc. The changes that have taken place in these, the concentrations of these in the last 150 years, and we put it, and we run the same model now with the natural forcing including it, and you see, lo and behold, now you see that the blue and the red line, they match with the black line. So, which shows clearly that the human forcing has, or human-made activities or human-made emissions have contributed to the current global warming or the increase in temperature very clearly. So, in the last 150 years, meaning 1850 to 2012, the Earth warmed by about 0.85 degrees centigrade. After that, it is warmed by another 0.5 degrees centigrade also. So, as we saw, that the rate of increase is also increasing in the last 150 years. Okay. When it comes to attributing the temperature change due to each of these species, this is the observed warming. And so the temperature change due to greenhouse gases, etc., you can actually rely on, and then you can say that, well, this is due to the temperature change due to the carbon dioxide, etc., or greenhouse gases. And we also saw that the natural forcing such as solar irradiance or volcanoes don't contribute anything. There is also a systematic variability, internal variability that is occurring in the nature in terms of the climate. That also does not produce any change in the temperature. But as we saw, very similar to the forcing that we saw before by the aerosol species, the temperature change can either be cooling or warming. So which means that they still, despite our enhancement in the knowledge, aerosols continue to contribute the largest uncertainty in climate. So we looked at, for example, in the indirect radiative, where the radiation can influence the cloud, etc. So here we are looking at the phenomenon which we are all familiar with is the Indian summer monsoon. So these are two contrasting years, it's 2002 and 2003, starting from June 1st to September 30th, the rainfall across India in millimeter per day. What you are seeing is actually the trend, or what is called as the normal here, and the day-to-day rain in the 2 years are shown here. So you can see that there is a large deficit in 2002, while there is a large increase in 2003. And the deficit is on the order of about 40%, the increase is on the order of about 8%. I mean, so what? If the rain is changing, etc., what is happening? So in these times when there is no rain, the aerosols that are produced by all these activities, they actually result in a build-up. So what if they build up? What happens? So here you can see the effect of these aerosols building up. So this is the drought condition. This is a normal or an excess rainfall condition. You see that the whole of India, actually you are seeing the values are more redder. It is the same optical depth figure that you saw before in the global map scenario, where the scale was from 0 to 1. You see that across the entire country, it is more of like red or yellow or something. In the drought year, which means that otherwise the rain would have removed some of these particles by gravitational settling or wet deposition. That did not occur because the rains were very much less. So contrast this with 2003, you see a lot of these reddish streaks in the oceanic region, and also in the up towards the northwest and north, etc. But most of the other regions, it is actually more cleaner. The values are lower. Not only that, when you divide this into, for example, the absorbing species versus the scattering species, you see that in 2002 there was a lot of absorbing species when compared to 2003. Now, this is due to the dust and the smoke that was present, which otherwise would have got removed because of the rain, but this dry conditions of non-occurrence of the rain can actually result in drier conditions, which will result in more smoke and dust scenario, and these can get uplifted into the atmosphere and can result in a higher amount of absorbing particles. That's exactly what you see here during 2002 vis-a-vis 2003. You see that the values are much lower. The higher values indicate there are more number of absorbing aerosols. So how does it affect? How does it show? I mean, the absorbing aerosols increased, this, that, etc. So what is shown here is the frequency of the cloud effective radius. The cloud effective radius beyond a certain micrometer, certain size, is actually a size after which rains will occur. This is the effective radius of the particles that is present in the cloud that you see. So the critical radius or the precipitation threshold is the cloud effective radius of 14 micrometer and larger. So when you do this, when you bifurcate this as the effective radius in several size bins, namely 10 to 14, 14 to 18, 18 to 22, 22 to 26, 26 to 30, you see that in 2002, over the country, there is much less number of frequency of occurrence of any of these sizes. In fact, you don't see sizes that are beyond 22 micrometer in the 2002 scenario. But contrast this with 2003, you see that almost 70% of the particles, the cloud droplets, the precipitation threshold radius was more than 18 micrometer, which means more amount of rain. So in July 2002, for example, 80% of the cloud effective radius was lower than 14 micrometer in northwest. You can see this here. In northwest, we are meaning Gujarat, Rajasthan, that belt, which is more drier when compared to the rest of the country. So where the anomaly also was 90%, highest rainfall anomaly, all India it was 40%. So you can see that this can lead to a reduction in the rainfall. So the aerosol leading to a reduction in the rainfall, the cyclic thing, reduction in rainfall leading to more drier conditions, resulting in more absorbing aerosols, and hence affecting the rainfall distribution. So as the optical depth and the absorbing aerosol component increases in the atmosphere during monsoon time frame, the cloud effective radius decreases, as you see clearly here, which is the observational evidence for the indirect radiative effect of aerosols. Now, the last component of this presentation is I mentioned that the volcanic eruptions are a major source of aerosols in the atmosphere, mainly in the stratosphere and also in the troposphere. These volcanic eruptions typically inject megatons of sulfur dioxide. 1 megaton is about 10 to the power 12 grams, mainly sulfur dioxide. They also emit water vapor, water, carbon dioxide, etc. But they are very small in number as compared to what you see in terms of the sulfide. The major eruption that occurred in the last 30-40 years, and the major eruption of the 21st century, occurred on June 15, 1991 in Mount Pinatubo, Manila, Philippines, at 15 degree north and 120 degree east. This is near the airbase that you see. It also injects a lot of ash, siliceous material, volcanic eruption. So what you are seeing is not the oil, but the ash that was found over the aeroplane that was there. And you also see, because of the weight of these ash particles, the aeroplane got tilted, which should have been like this. You can see that the weight kind of made an imbalance. And you also see this is all ash particles. That is, it's not snow. This ash particle that is near the volcanic site. The ash is thrown in large numbers in the lower altitudes. Otherwise, most of the material gets injected into the stratospheric altitudes, which will convert into sulfate aerosols, and then will have its own, because of this, the amount of particles that are present will contribute to, because these particles are scattering the amount of radiation that would have otherwise come in, it will create a net cooling here at the surface. And these particles in the infrared can absorb the radiation. They will actually heat up the atmosphere where they are present. Most of these are found in the above the tropopause, going all the way up to 30 kilometers or so. In addition to this, because of a phenomenon called as the, okay, we'll come to that. So if you look at the, after a major volcanic eruption, typically the surface cools by about 0.1 to 0.2 degree centigrade, as is seen here, and the stratosphere altitudes above tropopause will increase by about 1 degree at least. Okay. Now, when we look at the different types of particles, looking at the source, emissions, etc., are they directly related in terms of the amount of emissions, the loading that occurs in the atmosphere versus the optical depth, etc.? There is actually no direct relation. For example, if you look at the percentage of natural species in terms of sources, with respect to the loading, these both are higher. But if you look at the optical depth, which is the integral of the number of particles present between 0 to 40 kilometers, is actually more or less similar to what is produced by the humans. So this is where one of the challenges that occurs in estimating or differentiating the natural component from the man-made component of aerosols. This is still a challenge, because smoke from natural burning such as forest fires is considered as a natural component, but most of the times the smoke that occurs in the forest or the fires is actually not natural. These are man-made too. So if you look at why, if we know the three parameters we saw, the variations, for example, in the optical depth, the signal scattering albedo, which defines the chemical composition, and then the shape, which is the asymmetry parameter. So having known these, how any change of this, how it is going to affect the radiative forcing and hence climate, for example. So we do a trial experiment here. What we do is we take a standard case and then we increase the optical depth by 10%, let us say. And then we decrease the chemical composition by 10%, and we also change the asymmetry parameter by 10% or so, and see what is happening in terms of the radiation change, the change in the radiation. So with respect to the normal case, if you increase the optical depth, the change is 10%. Please note that this is a linear change. This optical depth increased by 10%, the radiation or radiative forcing increased by 10%. Now in the next scenario, what we do is that we change the composition. We make the aerosols more absorbing from 0.8 to 0.72. Now the change, for example, is about 22%. This is non-linear. Okay. The next thing I do is that I change the asymmetry parameter by 10%. So I make the particle to scatter more amount of radiation in the forward direction. Does it affect the radiative forcing? The answer is no, because the change is about 1% or lower. So of the three species that we talk, three parameters that decide the radiative impact of aerosol on climate or on temperature, the major thing is actually the chemical composition, in addition to the column content. And when you, so we saw that the temperature change in the, I mean, we did it with the different models, and we saw that there are changes that are occurring. And if you look at the changes, each of the model shows up differences, etc. And you can see that typically there are like two peaks that are found. The radiative forcing is actually high and strongly negative over the industrialized regions because of the emissions, namely Asia, Europe, and North America. Difference among the models is large, so simulating the radiative effects is still a challenge. That is contributed by the aerosol burden, the differences in the burden, how much of it is scattering or absorbing versus the content itself, the column content itself. The in the connecting the climate change with respect to the aerosol condition, all of you, I am sure, are familiar with the ozone, which is very important for survival of humans in the earth because it absorbs the harmful ultraviolet radiation. It is produced in the tropical upper stratosphere through oxygen photochemistry. But in the troposphere, because of this urban vehicular industrial pollution, ozone is produced, which actually results in what is called as the smog, which is nothing but the smoke plus fog. Now, through which ozone is produced in the atmosphere in the near surface. While the stratospheric near ozone that is near us is actually harmful, but the ozone that is far away from us, which is in the stratosphere, is actually pretty good. More ozone up is good, more ozone here is bad. So these volcanic aerosols that we saw, actually they can provide surface areas for the heterogeneous chemical reactions to occur, wherein when you have more aerosols, this is a stratospheric aerosol, just the increase that happened after volcanic eruption, which is due to the large amount of sulfur dioxide that was injected, which got converted to sulfate aerosols. You see that where there was an aerosol increase, there is a function of altitude. You see that ozone decreased significantly. So any increase in aerosol is synonymous with the decreases in the ozone. This is because the aerosol provides the surface area for these ozone depletion reactions to occur. On the global scale, the total changes in ozone, we know it has been decreasing because of the amount of chlorofluorocarbons that are present in the atmosphere, and the ozone has been decreasing, and it will try to come back to the normal position in about another 30 years or so. Because of Mount Pinatubo eruption, as you remember, occurred in June 1991. Because of this large increase in the amount of aerosols in the stratospheric altitudes, because of this heterogeneous chemical reactions taking place, the amount of ozone got reduced. You can see that significantly reduced in the years 92 to 93. So it is like I mentioned initially, change in any of the component of the climate system could directly alter the climate. It can also alter through changing the composition, other species composition, like it happens here. Aerosols increased, ozone decreased, but then it resulted in the ozone depletion and contributing to subsequent changes. So to summarize, for example, we looked at the climate system, the various components and the process. We focused more on the air pollutants or the aerosols that are present in the troposphere and the stratosphere. We also analyzed the concept of radiative forcing, the factors, the agents that influence the climate, and how the forcing is related to temperature. And what do we mean by climate change? The various facets of climate change and the features that contribute to the climate change. And briefly touched upon how ozone is also contributing to this change in the aerosol, and how aerosol and ozone in the stratosphere are interlinked, their increase or decrease contributing to forcing and hence its effect on climate. So with this, I think I will say thank you, and I'll be happy to answer any questions.
Thank you, sir. Thank you very much for your nice presentation. Now the session is open for discussion. Dear participants, please interact with the professor for any queries, any clarifications. Thank you.
Good morning, sir. It was an interesting presentation. I have a question to clarification to ask him. The earlier part of your presentation, you mentioned how the size range is between 0.1 to 1 micrometer. Is that determined by the gravity? For example, if in case of Earth, because of the gravitational force, is that the crucial point which determines the flotation rate or the retention time in the stratosphere or the troposphere? For example, if we compare to another planet which has a lower or higher gravity, will that particular matter range of size range differ?
No, the size range is not determined by the gravity. The size range is determined by the production mechanism and the source, which whether it can produce fine particles or whether it can result in coarse particles.
Okay.
Now, once this is formed in the atmosphere, then there are two questions that come: where it is formed, whether it is formed in the lower altitudes or whether it is formed in the higher altitudes. And you combine this with the size. For example, at lower altitudes, where you feel the effect of gravity more than higher altitudes, and if the size of these particles are larger, then obviously the effect of gravity will be more seen more, and it will get reduced. It will get removed from the atmosphere. Suppose if I inject particles like it happens after a volcanic eruption, the particles that are injected are actually gaseous molecules, are very much lower in size. They combine with the sulfur dioxide, for example, will combine with the water vapor and form sulfuric acid droplet, and then will form sulfate aerosols in roughly about a month's time. Now, once these formation mechanism that it is happening, it is also happening in the lower atmosphere, because sulfur dioxide is emitted by all the vehicles, all the industries, etc. It will also combine with the water vapor that is present in the lower altitude. It will form sulfate aerosol, typically in smaller sizes. But here what happens is, because they are nearer the surface, by gravitational settling, they will settle within a week's time. But the same particle, when it goes up to 25 kilometers, the settling velocity changes, and it typically takes roughly about 3 years for that particle to come down, if it maintains the same size. But then once you are in the atmosphere, there are microphysical processes that keep happening, like nucleation, coagulation, condensation, growth, etc. So they will also grow in size, and then they will start kind of diffusing or start settling from the higher altitudes. They come down, and when they come near the surface, they will feel the effect of gravity more than what they were feeling above, and they will settle. But so it is a question of where it is formed, what size it is, and that is determined by the settling. That will decide the time.
Thank you, sir. So if that is the case of where it is formed and how it is distributed, being an ellipsoid shape, so there is a higher instance of centripetal force in the equator when compared to the polar region. Does that explain why higher aerosol concentration is maybe present in the polar regions compared to the equator? Or
higher, tell me again, higher concentration in the polar region.
Would there be instance of that case? Because of the higher gravitational force? Will that
No. See, you should understand that aerosols are produced by sources. but that are present in the Earth's surface. And once they are produced, they also get transported. If you go to Arctic or in the poles, for example, the sources are much less. It's only the transport of the species that is produced from different parts of the globe, they get transported. So there is no a major source except for the ocean that is there near the poles.
Thank you, sir. So we have some more questions from Mr. Nahar Muhammad. It's in the chat box. I'll paraphrase it for you.
Yeah.
Dear Professor, I found your session quite insightful. As someone who works in the area of forest and conservation, I'm curious to know the linkage of forest and aerosols and their significance in the Indian context.
Okay. So I actually because it was about 1 hour or so, I did not touch upon the effect of aerosols on, for example, agricultural aspects. So the same effect that you see, for example, the scattering and the absorbing, reducing the amount of radiation that is reaching the Earth's surface. Imagine this happening on a leaf surface or something like that. Then it will actually affect their photosynthesis and photolysis rate, etc. So model studies have shown clearly that when the amount of radiation that would have reached normally, when you alter the balance because of this aerosols or pollution that is put into by scattering and absorption, the yield will always reduce, of be it rice or wheat or something. It is the same that happens in the forest also. So when you kind of remove a lot of forest, etc., you are actually making a source of aerosols. There are studies which clearly indicate that when you a forest area, when you are trying to convert, you are actually changing the land cover and making it a more dry region, which will inject a large amount of dust particles. So everything is connected in a way. Any change in this concentration will have an impact on the forest cover, etc.
Thank you, sir. There's one more question from Mr. Muralidharan.
Yeah.
Sir, ice albedo with higher reflection is a positive feedback. What about the increased reflection of thicker clouds with dense nuclei of pollutants? How do we consider with regard of global warming?
Okay, this whole phenomenon is actually a complex process. I made it a little simpler here. When it comes to the ice albedo with feedback and the cloud with nuclei of pollutants, etc., there are a few other effects that occur, namely the glaciation effect or the ice nuclei effect or the thermodynamic effect, etc. All of them, they are dependent on or a function of the temperature of the cloud particles, size, etc. And all of them have a large range of uncertainty, including the positive feedback that he mentions here. So in general, we know that clouds are a major cooling agent in the Earth's atmosphere. But these are the reasons why we have a large uncertainty when it comes to the cloud radiative effect because of this.
So we have one more question from Swapna Dire.
Yeah.
It was very good morning. It was a very informative session. I would like to know how these aerosols affect wildflower rather than influencing climate change. Is there any disease among wildlife species that caused due to aerosol effects?
I have come across certain studies, but no, I am not very familiar with this. But it is like this. You are okay. Let me rephrase it in a different way. Just after the volcanic eruption, for example, in 1991, June 1991, as I said, these sulfate aerosols, for example, will actually produce cooling for the first 6 months to 1 year. So this cooling was felt at the Earth's surface, including all tropical countries across the globe. Now, the effect on this thing was the polar bears, for example, because of the cooling, the ice melted a little later than normal because of the cooling. Otherwise, the temperature would have increased. The Greenland ice would have melted earlier. Now, it actually resulted in a kind of a fatter, a bigger growth of bears, and they are famously called as the Pinatubo bears because these bears, polar bears in the high latitudes were thicker, bigger, fatter than the normal bears. And the second thing that happens in the ocean, for example, because of this cooling, the ocean circulation itself can get affected, and because of this, the mixing that takes place normally would not happen. So this can actually result in smothering of corals, etc. Because the algae bloom was unprecedented, so it can actually smother the corals. So there are studies, the large scale effects of these pollution when they are across the wildlife on a larger time frame. So like it need not be directly aerosol contributing to any effect that the aerosols produce would actually contribute to a change in like we saw in the forest as well as in the wild fauna and flora.
We have one more question from Karthik Venkatraman. Since we predict the future scenario of radiative forcing and climate change using models, but still the models are suffering from external factors and evolving, okay, how will it impact our policies toward climate mitigation and what can we do about it?
Okay, there are a few things that we have to understand here. When you predict the future scenario of climate change, etc., first the models are tested for reproducing the current scenario. So once the models that are scientifically confident of producing the real-time atmosphere of the climate as of now are used, which are like tested, calibrated, and compared with other results, etc., they are used for predicting the future scenario. So this aspect of models predicting for the future is actually taken care of by this effect. Now, when you say model, the model is a realistic model or a good model is a realistic representation of all the factors that constitute the climate system, which we know it consists of everything: land, surface, ocean, atmosphere, hydrosphere, cryosphere, etc., and the interactions between them. So the variation among the models or the variation among the results of the model come from the different processes, how they are accommodated, how they are parameterized, how they are represented, etc. So there can be variations, there can be deviations, which we saw that when we looked at the temperature, for example, all these 30 models, they are not falling on the same line, which is the mean line which you saw in thicker form, but different models, they kind of were around this mean value. So overall, we know that whichever models we have used for predicting the future thing in terms of either increase in the CO2 or pollution or changes in precipitation, etc., are reliable. That answers the first question. Now, so then the second factor is the internal variability. So the internal variability, we are able to document it very clearly, and we have also determined that the changes due in the climate due to internal variability changes are actually negligible or very, very small. So the climate, when you say that it is changing, or the climate change prediction is only by the external factors, which keep changing. So what is done is, so then we adapt to what is called as the different scenarios. For example, one who is familiar with the IPCC assessment, for example, in the last report, we came up with what is called as the representative concentration pathways, or RCPs for short. So what we did is earlier we were projecting this as scenarios, for example, A1, B1, A2, B2, and all that. So instead we changed that to now representative concentration pathways. So this is like scenarios when, for example, CO2 is increasing in this rate, then that is called one scenario. When and the resultant radiative forcing that will occur, which is actually called 2.6. So there were like the RCP scenarios where RCP 2.6, then RCP 4.6, then 6.2, 8.5, etc. So each of these indicate that if the concentration keeps changing of CO2 and other gases, if they keep changing at the scenario that we have seen before, and the variation, how much the global warming or the change in temperature will occur. So these models, the same models that predicted the other scenarios, and they were really representing more or less the climate system that we know of, they are projecting a range of increase in temperature between 2 to 6 degrees with the different scenarios that are involved. Starting from 2.6 to 8.5, the Earth will be warmer by 2 degrees centigrade to up to 6 degrees. Okay. Now, these predictions or the scenarios are used to govern our impact policies so that can lead to the mitigation. So these inputs are shared with the policymakers and the governments, etc., to frame the mitigation policies and future action on it.
Thank you, sir. There's one more question. Are there any key difference between precipitation and rainfall? Excuse me, sir. Sorry, you've been muted accidentally. Can you please unmute yourself? Thank you.
Okay. Where any form of deposition, be it snow or water, is actually called precipitation. So when you say rainfall, you are talking about a form of precipitation.
Thank you, sir. Sir, I have one more question. How do models reliably obtain data, climatic data from 19th century or say like 1850?
Okay. As far as the temperature data is concerned, which is maintained by the World Meteorological Organization and a few other country organizations, just like our India Meteorological Department in case of India. So these are temperatures that are measured since 1850 or so, maintaining the same instrument, doing very regular calibration, quality control checks, etc. These all form the inputs to the climate change scenarios and also for this thing. So these are kind of highly reliable, highly accurate data. So that is why we are able to see or find out changes that are even in the range of about 0.1 degree centigrade or something, the change in the temperature at several locations. So what you saw in the global map, when I said the trends are changing, etc. So it is not that it is uniform, the change in temperature, as you very well are aware. The changes are more in certain regions, while the changes in temperature are less in certain regions. So each of them we are able to document. That is because of the temperature data, that reliable, highly quantified, calibrated, reliable data set that is available across the globe from courtesy many of these meteorological departments, divisions, etc., or research or institutes that do this research. Prior to that, the ice cores that are deposited in the high latitudes or poles actually give information about the temperature structure. Again, this has a linkage to the sulfate aerosols that are produced by volcanic eruption. The sulfate aerosols that are produced by volcanic eruption, they get transported across the globe. And so once they get transported to the higher polar regions where there is a lot of ice and core, etc., they actually get settled on the ice. And they preserve the signature of the amount of sulfate that is produced that was due to each of this eruption. So if you looked at the if you remember carefully the temperature change that occurred, I also showed temperature changes even before like 1850, etc. These all information came from such analysis of ice core data in terms of the global temperature change. So that is how we do the temperature change analysis.
Thank you, sir.
Thank you, sir. Participants, is there any questions? Participants, any questions? Any clarifications? Okay, sir. If there is no questions, we thank our Professor Dr. Ramachandran for his excellent presentations. And sir will give another presentation. Yes, it's a practical. It will be by 12:10 p.m. Okay, sir. We will meet by 12:10 p.m. Okay, sir.
Okay. Sure.
Okay, sir. Thank you, sir. So participants, meet back by 12 p.m. 12:10 p.m. Okay. So we have a 15 minutes break. So we have a 15 minutes break. So please come back. Thank you.
Excuse me, sir. Sir, you are still presenting your screen. Can you? Thank you, sir.